Hello, Math 153. What we're looking at today is 11.6 events involving not and or. These are going to be two keywords that we want to look for in our problem. This is going to be the word not and or. We have three objectives here, but we're actually going to cross off the last one. So what we're going to be looking at is going to be find the probability that an event will not occur, and then find the probability of one event or a second event occurring. And like I said, this last one, understand and use odds, we're gonna cross that one off our list for this semester. So let's go ahead and start with the first two things. So the probability of an event not occurring. We know P of E is the probability of an event E. Well, we say P of not E is the probability that the event E will not occur. So if we take the probability that an event will occur and we add it to the probability of the event not occurring, together they equal 1. We call these two things here, we're going to call these complements because together they add up to 1. So what we're going to do is looking at solving for P of E or for P of not E, we can obtain the following formulas. So looking at this formula we just created, if we were to start by just solving for, let's solve for P of E, we can take this whole second part of this and subtract it and move it to this side. You'll notice my little Star Wars pointer here. So like I said, we can subtract the probability of the event not occurring to the other side. So therefore, we could say the probability of the event occurring is going to be equal to 1 minus the probability that the event does not occur. And we can also do the same thing and solve for the probability of it not occurring, meaning we can take the probability of that event occurring and move it to the other side. So we're taking the probability of the event not occurring, and that's going to be equal to 1 minus the probability of the event occurring. Now we're going to see how we're going to use this in the next couple examples. So the first one here, if you're dealt one card from a standard 52 card deck, we want to find the probability here that you are not dealt a queen. So we'll find the probability of not being dealt a queen. So we want to find the probability of not being dealt a queen. That's what we want to think about. So using the formulas from above, we actually want to look at this second one here because we want to find the probability of something not occurring. So we want to take 1 minus the probability of the event actually occurring. So we're going to say, okay, this is going to be equal to 1 minus the probability of getting a queen. Now I'm going to come over to the side here and do some scratch work. We need to find what this probability is of getting a queen. So finding the probability of getting a queen, that means we want to find how many queens are there in a deck of cards divided by the total amount. We know that in a standard deck of cards there are 4 queens at a total of 52 cards, which simplifies to 1 over 13. So now what we're going to do is substitute 113 in for the probability of getting a queen. So we're going to say, okay, that's 1 minus 1 over 13. Now, you can use your calculator to do this. That's what I would recommend, that's so you don't make any mistakes. Or we can rewrite 1 as 13 over 13. The reason why I chose 13 is because that's what my denominator here is. So I'm just rewriting 1 as whatever that value would be there. And then we want to continue on with subtracting 1 out of 13. And we just subtract across the numerators. 13 minus 1 would be 12 out of 13. This would be our answer there. Now, you may have thought, but wait, did we have to do all that? And the answer is no. So do I have to use this formula that we just used to solve that? And the answer is no there. To find the probability of not getting a queen, we could have also have taken a similar approach to what we did right here. We could take, okay, we would just want to find how many cards in the deck are not a queen and divide that by the total number here. Well, in a deck of cards, we know that the 48 of the cards are not queens at a total of 52. Simplify that, you get 12 out of 13. So you can see that we are getting the same answer no matter which approach you choose. Okay, moving on to the next page. Example 2, using the complement rules. Now we're going to be looking at a picture here and applying the same things. So we see the circle graph in the figure above shows the distribution by age group of the 191 million car drivers in the US, with all numbers rounded to the nearest million. If one driver is randomly selected, find the probability that the person A is not in the 20 to 29 age group and B is less than 80 years old. Express probabilities as simplified fractions. So we have two parts to this one. We're finding two different things. So we'll start with part A. So sorry about that. Let's undo this. There we go. Again, my apologies. Okay, so the first one in part A is we want to find the probability that they're not in the 20 to 29 year age group. So using the formulas we looked on the first page, we want to do 1 minus the probability that they are in that age group. So we need to find that first. So we need to find the probability that they are in that age group. So if we go up to our picture up here, we find 20 to 29, which would be right here. We see that there are 33 of those. So we know that there's 33 million, and it tells us out of a total of 191. So that's the fraction we have to substitute in for that probability. So we have to do 1 minus 33 over 191. Again, you can use your calculator. I'm going to change 1 to be 191 over 191. And we're subtracting 33 over 191. Subtract across the numerators, 191 minus 33 is 158 divided by 191. Make sure that doesn't simplify, and we leave it as that. Okay, part B. Part B, we want to find the probability that the person is less than 80 years old. So we want to find, again, using the formulas from the first page, we want to find 1 minus the probability that they're not less than 80, which means that the probability that they are greater than 80 years old. So we need to first find out how many are greater than 80 years old. So going up to the pie chart that we're looking at out top, let's get rid of this since we're done with that. Looking at the pie chart from above, we want to find how many are above 80. And it looks like we find that there are 6 million out of a total of the 191 that are going to be above 80. So we have 1 minus 6 over 191. Again, I'm going to rewrite the form of 1. And then we want to subtract across the numerators to get 185 over 191. Again, make sure your fraction is in its simplified form, which in this case it is. Okay, let's move on to the next page. Okay, what we're talking about now are probabilities with mutually exclusive events. So you want to make sure you really understand what this means, this mutually exclusive. What mutually exclusive events are it's events that are not able to occur simultaneously. So what it means is it's impossible for events A and B to occur at the same time. So what this means, for example, if you were to pick a card, so example, pick a card out of a standard deck of cards. When you pick a card, there is no way that card could be a 3 and a 4, for example. Pick a card, we say it cannot be a 3 and a 4. Or example, you roll a die. You can't roll a 2 and a 3 when you roll the die. So these would be mutually exclusive. It's when you have two events that's impossible for them to occur at the same time. So when we're talking about finding the probability of these mutually exclusive events, we want to find the probability of event A occurring or event B occurring. And what we have to do is take the probability of that event A and add it to the probability of the event B. So let's go ahead and look at an example here. We want to find if one card is randomly selected from a deck, what is the probability of selecting a king or a queen? Now, we know here that these events, a king or a queen, these would be mutually exclusive because they cannot, let's see, that should be an either exclusive. There it goes. These cannot happen at the same time. You can't choose a card and it being a king and a queen. Therefore, they are mutually exclusive. So what we have to do is use the formula. So we want to find the probability of a king or a queen, which means we need to find the probability of getting a king and add it to the probability of getting a queen. Now with the deck of cards, let's actually go ahead here and do some, we'll use the red here and do some side work. We want to find the probability of getting a king. So we want to find the number of kings over the total amount of cards. We know there are 4 kings in a deck out of a total of 52, which we know simplifies to 1/13. The probability of getting a queen, same idea. We want to take the queens over the totals, which is going to be that same probability of 4 out of 52, which is 1/13. Now what we can do is take both of these and substitute them into our probability formula we're working with. So we want to take the 1/13 probability of getting a king and add it to the 1/13 the probability of getting a queen, add them together to get 2/13 is the probability of selecting a card that's a king or a queen. Again, mutually exclusive is 2 events that cannot happen simultaneously. Okay, one last page and we'll be finished up with 11.6. Is the same thing that we did in the previous page. Now what we are looking at are events that are not mutually exclusive. So yeah, make sure you understand the difference between mutually exclusive and not mutually exclusive. Not mutually exclusive are when you can have 2 events. So we can have events A and B, and these can both occur at the same time. So they can occur at the same time. So for example here, what we can say is you can choose a red card that is a king. So if you, again, going back to the deck of cards, pick a card, red, and a king. You can pick a card that's a king and a red. So it can happen at the same time. So when we need to find the probability of 2 events occurring when they are not mutually exclusive. So now we want to find the probability, let's go back to the blue here. So we want to find the probability of A or B, but this time they're not mutually exclusive. So we want to take the probability of A and add it to the probability of B, which you can see, but now what we have to do is subtract out the probability of them both occurring. So we have to take away ones that hold both of them. For example, take away the red queen or the red kings with what I just talked about. So let's see how this is used in an example here. So with example 4, you randomly select one card from a deck of cards. What's the probability of selecting a diamond or a picture card? Now, picture cards, if you're not familiar, they're jack, queens, or kings. So we want to know what's the probability of getting a diamond that has a picture on it. Now, these are not mutually exclusive because you can pick one card that has both of these things on it. So we want to find the probability of selecting a diamond or a picture card. So what we have to do is find the probability, and we can think of this as event A and event B. So the probability of getting a diamond, I'm going to abbreviate it and just say dia, and add it to the probability of getting a picture card. Now we have to subtract the probability. We want to subtract out the probability of a diamond and a picture card. Again, we're going to look at each of these strings separately and then put them back into the formula. So the probability of choosing a diamond. Well, this is where we need to be familiar with our deck of cards again. So we want to figure out how many diamonds are there out of the total deck of cards. Well, there are 13 diamonds out of 52. Now we'll notice that that reduces, but I'm going to hold off on reducing that just for a moment. And then we want to find the probability of a picture card. We said that we want to take the picture cards divided by the total. Well, picture cards are Jack, Queen, King, but we have 4 of each of those because you have 1 in each suit. So therefore, we have 12 altogether because you have uh, Jack, Queen, King's 3 out of 4 different suits. 3 times 4 is 12. Again, out of a total of 52 cards. Now what we have to do is find the probability of it being a diamond and a picture card. So we want to find out how many diamonds have a picture on them out of the total amount. Well, we know that there would be 3 that are diamonds because you can have a jack of diamonds, a queen of diamonds, and a king of diamonds. So that would be 3 out of 52. Now what we want to do is use these 3 fractions here to substitute them into this formula. The reason why I didn't reduce is because I want them all to have the same denominator. So we want to take 13 out of 52 and add it to 12 out of 52 and then subtract the 3 out of 52. So 13 plus 12 minus 3 would give us 22 out of 52, but we know that would simplify into 11 out of 26. So that would be the probability of getting a diamond or a picture card. Let me know if you have any questions on anything, and good luck on your homework.